Before we start building prey-predator models in InsightMaker, let's just quickly review the concepts of functional response and numeric response, because these are really important concepts in prey-predator modeling. The functional response is just what we see here. This is a function that represents the total prey eaten per predator per time step as a function of the number of prey that are in the landscape. All right. So the functional response is the per capita per predator rate of consumption per time step as a function of the total prey availability. The more prey that are available in this really simple model, the more the prey are eaten per predator. All right. This is the simplest possible functional response. We'll go through some additional functional responses later that are a little more realistic. And then the numerical response looks a lot like the functional response, but it is a model that basically, predicts the increase in the per capita growth rate of the predator population due to prey consumption as a function of the victim abundance or the prey abundance. The more prey abundance there is in the landscape, the greater the increase in the growth rate of the predator population due to prey consumption. All right, that's the numerical response, essentially the conversion of all the eating that's going on, all the prey, the victims that are consumed, and converting those into new predators using the per capita rate of growth for the predator population. All right. What we're going to do next is model the functional response and the numerical response for the Lotka-Volterra prey-predator system, and we're going to do it in InsightMaker. So please scroll down to the InsightMaker link where it says LV or Lotka-Volterra predation model in InsightMaker. Clone this insight. All right, that insight should look something like this. All right, so just make sure you clone that base prey predator model so you can make changes to it. You'll note that the model is largely constructed for you. We have a functional response and a numerical response variable. We have the alpha term, we have the beta term, we have a prey population, a predator population. And some of this has already been filled in for you because you already know how to do this stuff. Like, you know how to take a per capita intrinsic growth rate and build an exponential growth model by multiplying that by the total population abundance. And we've already done that. So that's already filled in for you. That's the growth rate of the prey population in the absence of predators. And here's the growth rate of the predator population in the absence of prey. It's the same thing. You multiply the predator population times this exponential growth term, but this exponential growth term happens to be negative because this is an outflow, right? So this is the loss of predators due to natural mortality, and in the absence of prey, the predator population will go extinct. Let's run the model and just make sure that this happens that this is realistic considering the model that we're just put together and the fact that there is no interaction between prey and predator yet because we have to put that in. Here is the prey population growing exponentially to absurd numbers because it's exponential growth. And then if we look at the predators, they go from 10 and they decline exponentially to 0 because there's no interaction. They cannot eat any prey at this point, so they're going to decline to extinction. So far, that looks pretty good. You'll note that this is not filled in yet. That's the influx of new predators due to prey consumption. And this is not filled in. That's the total prey consumed by predators. Let's fill it in. First of all, let's consider the functional response. The functional response is, like we've seen before, is the per capita rate of prey consumption per time step as a function of the total prey in the landscape. So we have to take the total prey in the landscape. That's obviously part of this. and we multiply that by this alpha term, right? And so it's this linear relationship. The more prey there are, the more prey are going to bump into predators randomly, and more prey are going to be consumed per predator. So that is the simple functional response model. Alpha times prey, or prey times alpha, doesn't matter. And let's compute the total prey consumed. All we have to do is take that functional response and multiply it by the number of predators, because the functional response is per predator, right? That's the prey consumed per predator as a function of the total number of victims. Now we have to multiply that by the total number of predators, and that gets the total number of victims consumed per time step, and that is our model. So for functional response, it's just alpha times prey, and for total prey consumed, it is the functional response times the total predator population. That's one half of the equation. Now we have to do the numerical response. The numerical response, you have to take this beta term and multiply it by the total prey population. The beta term basically is defining the degree to which the growth rate of the predator population increases for every prey in the landscape. You multiply it by the total number of prey, and you get the total amount by which R for the predator population, or the intrinsic rate of growth for the predator population, has increased due to prey consumption. And that is the numerical response. So now all we have to do is fill in the predator growth rate. Now to do that, you take the numerical response, which is kind of like R, kind of like an intrinsic rate of growth, and you just have to multiply it by the total predator population to get the total influx of new predators into the population in this time step due to prey consumption. That is this flow that we are interested in parameterizing here. And once we do that, we have a fully fleshed out Lotka-Volterra prey-predator model. And now I encourage you to play around with this model. First of all, simulate this model and see what happens. We have a oscillating prey-predator dynamics, which we'll talk about in just a few minutes in the state space. But take a minute and play around with some of the parameters and see what kind of dynamics you can get. Like, what if you reduce the intrinsic rate of growth for the prey population? Well, you still get something, but it just goes a lot slower. It's still kind of interesting. So take a few minutes to play around with it. If we go back to the lecture, we'll see that there's some questions that we can address. We can change the simulation length to 200. That's one thing we could do. We can set the initial abundance of prey and predator to 150 and set the alpha and beta terms to 0.001 and set the R prey and Q pred terms to 0.1. So let's try to remember those things. We'll go back into this model here. I think the alpha and beta were both going to be set at 0.001. 100 prey, 50 predators, and the R and Q are both 0.1. Did I get that right? Let's look at that. Yeah, 0.1. All right. Let's see what happens here. And let's set this simulation length to 200, and let's do it. Nice. Just more like a sine wave type oscillating pattern of prey and predators. You can see which one's the prey. This is the prey. This is the predator. As the prey goes up, the predator starts to grow exponentially, but at some point the predators get to so much that the prey population really is heavily controlled. At a certain point, the the predator population can't grow anymore. It starts declining. At a certain point, the prey population can start increasing again because there aren't very many predators on the landscape. So we have this oscillating pattern that is common to the classic Lotka-Volterra prey-predator system. In step 6, it says to add a new display to represent the phase plane. So it's asking us to use Insight Maker to actually visualize what's going on in the phase plane. So let's do that. Let's go back here and we'll add a new display. This is going to be a phase plane display. And we're going to choose a scatter plot, which we've not used before in Insight Maker. We'll put prey first, and then we'll put predators second, and we'll apply, and we can see that we actually have a phase plane with prey on the x-axis, predators on the y-axis, and we can see what's going on. If just so you know that it's kind of moving this way in time. So prey increases, predators are increasing, but the predators now are controlling the prey, and so on and so forth. So that's the way the system is moving in time. We'll visualize that in R in just a few minutes. But again, take a few minutes to play around with this Lotka-Volterra prey-predator model. Try some additional parameter values for alpha, beta, R, and Q. And here's a couple of questions. Does the prey or predator ever go extinct? Or can they both coexist in this model? Are they always coexisting? Can you find some values of these parameters that make the prey or predator go extinct? Can you find some settings that make really slow oscillations? Well, we already saw one. Can you make some settings that make really fast oscillations in time? Can you find some settings that make very shallow oscillations? That is where there's not much of an amplitude to the oscillation, and that might, have more to do with the starting population sizes of the prey and predator. But this is a good chance for you to take a few minutes and play around with this model in Insight Maker, and then we will move on to prey-predator models on the phase plane.